Okay, this is video number 4 on refraction. We have had our introduction. We did Snell's law, extending Snell's law, and we're now going to do video number 4, or I'm going to do video number 4. And video number 4 is something called total internal reflection. And I'll say that again because I'm writing it, total internal reflection. This is not the word refraction, this is the word reflection, and reflecting is all to do with light bouncing off mirrors and shiny surfaces and things like that. Okay, to save me writing total internal reflection, and I know this is video number 4, to avoid total internal reflection, I will be referring to something called TIR, or just TIR. You should really, you remember, you're only going to get one question, possibly, on total internal reflection. Not every topic gets a question in the exam. But you're only going to come across one question. You're not going to see things again and again and again, like I have been doing in these videos, giving you loads of examples. If you're going to write down, if you get a question on total internal reflection, you're going to have to write down the words total internal reflection for the very first time, like I've done, and then abbreviate it afterwards. So you could write in a question total internal reflection, and then you could put TIR, and then you can use the letters TIR thereafter, and it saves a little bit of time doing that. So what is total internal reflection? Well, again, if you were in school, we would be looking at an experiment, but I'm going to describe this experiment, and I'm going to use a semicircular, move that down the page a bit. I'm going to use a semicircular block of glass, and we've seen a semicircular block of glass before, but this time I'm going to shine the light in, not through the straight side. Earlier on, before, I had rays of light coming into our block and then out, and they came out in a straight line. There's only 2 angles to look at, unlike a block. I went through all that before. This is the same, but this time we're going to shine the light in through the curved surface, and I'm going to aim, I'm going to put in my normal line, I'm going to aim the the beam of light, I'm going to aim the beam of light for the center point, just like I did before. Now here comes the beam of light. I'm just going to move over a little bit to draw this. Here comes a beam of light. Let's just draw a beam of light doing this. Okay, and what it's going to do is, on its way out, it's going to, it's going quite slowly here. It's going to be straight. It's going to be going quite fast, 3 times 10 to the power of 8. Gets in here 2 times 10 to the power of 8, but it's hitting straight on, and at that particular point it's 90 degrees, and it's going to go straight on, and then it's going to be going slower, but when it comes out, it's going to speed up. So it's going to bend away from the normal, and it's going to do something like that. So I'm going to have this block of glass, and we're going to look at what happens when we shine rays of light in at different angles here, different angles. So I'm going to redraw that, and I'm going to use different colors. If you've got different colors, great. And if you haven't, there's my semicircular block of glass. There's my normal line. And I'm going to start with a number of different rays at different angles coming in. So I'm going to use some different colors. So here's, it's not quite semicircular, is it? Oh, that's supposed to be straight along there. I'll just redraw mine so it looks nice. As long as yours looks reasonable, that's okay. Right, so there's my normal, there's my block of glass, and I'm going to draw a ray of light, which is going to come in here at an angle of, say, this is the blue ray. You could call them rays. I'm going to draw a number of different rays. I'm going to call this the blue ray or ray 1. If you haven't got colors, it doesn't matter, which I'm going to do in blue. And I hope the colors are coming out on your screen. Okay, so what's that ray of light going to do? It's going to pop out here somewhere like this. Okay, and my ray here, my theta angle here for my ray 1, which is blue, I'm going to say that's coming in at 20 degrees. Okay, and it's going to exit the block like that. Now what's going to happen is as this beam of light, I'm going to move it around, I'm going to shine it in there, I'm going to shine it in there, I'm going to shine it in there. This is almost the same as when I did Snell's law in that second video. I'm going to change the angle, I'm going to increase the angle as it comes around. What happens here is if I increase this angle here, call it angle X, if I increase this angle X here, as this beam of light comes round to say there, this exiting beam is going to move up here a little bit. Okay, so let's do say a green. I wonder if this green pen's working. I'm going to move it round. We'll stick it around here somewhere, this green one. That's okay, that looks good. So I've got a green ray of light and it's going to exit somewhere like this. And I'm going to have ray 2, which is in green, and that might be 30 degrees. Okay. And then I'm going to increase the angle. That was 20. It's now 30 for the green one. I'm going to increase it again. And as I start increasing this angle, as I go round, that one would have gone straight out. If I'd done one there, that would have gone straight out. This one's getting bent as it comes out. This one's getting bent more. As I go round here, slowly, 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 as I start to shine this ray of light round here, then this exiting ray is going to approach the boundary between the glass block and the air. So the next one I'm going to do, and I'm going to say this advisedly, the next one I'm going to do is about, this is orange, ray 3 is going to be orange, and it is about, that says about just, it's about 40 degrees. And what happens is it's going to come out directly along there. It's going to come down there. It's going to exit in line with the glass. Okay, so that's ray 3. Lastly, let's see if I can get a purple beam of light, and the purple beam of light is going to come in here. Well, I've got 20, 30, 40. We'll make this one 50. How about that? So here's a purple one. I don't know whether you can see this color here, purple. Number 4. And it's going to be 50 degrees. 50 degrees all the way around there. So I've got 20 degrees there. The green one is measured round to there. From the, all angles are measured between the normal and the ray of light. That's 30. The orange one from the normal all the way around there is about 40. And the purple one all the way around there is 50 degrees. So you could do this as an experiment in class, and you could find out. The reason why I've said about 40 is that it's not quite 40 degrees. It's not as nice a number as that, but you'll see that as the beam of light is moved round and round and round, it goes from there to there to there. What does this purple one do? Well, the purple one, if you can work this out, the blue one comes out, the green one comes out, and this angle is even bigger. The orange one comes out, and its angle that it comes out is actually at 90 degrees. And the purple one is reflected inside, and it's as if this inside surface here is a mirror, and this is what's called total internal reflection. It's where the beam of light doesn't come outside anymore, it stays inside the block and reflects back inside the block. So the purple ray of light is actually doing this thing called total internal reflection. All of it is getting reflected inside. And if you're wondering why don't we just call it internal reflection, the total bit is due to the fact, and I haven't put this on yet, is that there will be, when this blue ray 1 comes out, there will be a small amount of light that is reflected back up here from the blue ray, a small amount, and it will be quite faint. I'm going to draw that like a little bit faint, and it's about 10%. You'd get 10% of the beam of light is internally reflected, and about 90% comes out. As you go to the green ray of light, the green ray of light is going to, some of it in reality is going to get reflected, and it's gone up this time. It's about 30% is reflected back up here, and I'll try and do this one. The green one's going to be about here. I'll try and do it faintly. We're going to have about 30% or something is going to get reflected inside, and about 70% is going to get refracted out. So that's 10% and about 30%. The orange one, some of it again is reflected, but it's going to be more. You can see that it was 10%, 30%. This is about 60 or 70%. I don't know the numbers precisely, but is that going to be at this? It's not really at the same angle. Reflected angles are equal. Let's see if I can do this one about here. Okay, 10%, 30%, 70% is reflected inside, and about 30% comes out there. But the purple one, none of it comes out into the air straight away, and the purple one, 100% of that beam of light gets reflected inside the block, and that's why it's called total internal reflection. You can probably work this out, that the blue one's called partial internal reflection, 10%-ish, say 30%, say 70%. These are the rays of light that come out. You'll get the beam of light gets split into two, and it will be partial, some internally reflected and some externally refracted. By the time you get to quite a big angle, 50 degrees, then all of the ray of light, it's in glass here, all of the ray of light, 100% gets reflected and returned inside the block. None of it gets a chance to come out of the block straight away. Okay, small angles, some low amount, 10%-ish, large amount refracted, small percentage reflected, large amount refracted, a bigger percentage reflected, smaller refracted, bigger still, 10, 30, 50, by the time you get round here, all of it stays immediately inside total internal reflection. Okay, total internal reflection. Right, let's just sort my pens out now. And what are we going to do about some notes? Get rid of those and keep those. Okay. So we're going to give you some notes now. We're going to say the ray 1, which was blue. I've just drawn it in blue. It doesn't mean it's blue light. Let's get that clear. It's just a beam of light. It's a beam of light, and I've just color coded them so you can see what's going on. So ray 1. Okay. It's the 20-degree beam. And about 10% is internally reflected. Which means that about 90% emerges. 90% is refracted out into the air. And that just does the normal rules of Snell's law. N is sine theta 1 over sine theta 2. Now, I didn't say this earlier, but it's theta 1 outside. It's always theta 1 outside. So this angle would be theta 1, and it's theta 2. So theta 2 is 20 degrees. And you could do the calculations. You could say, right, I know the refractive index is 1.5, so I could do N is sine theta 1 over sine theta 2. Sine theta 1 is this angle here outside. And I could work out that angle outside if I need to do so, or if you were instructed to do so. But we've seen enough of those calculations. 10% internally reflected. So this is partial internal reflection. I'll skip the green one because it goes up to a higher percentage. I just want to show you what happened as you start moving the beam of light round like that. Ray, I won't write this in orange, but ray 3, which is about, keep saying about, because it's not quite exactly 40 degrees, and we'll come on to that. About 40 degrees, the 40-degree ray of light, that comes out along the edge. That comes out along the edge here, along a ledge. Could be a man standing there, person standing on the ledge. Don't know why I said that. That's going to come out along the edge of the block. Okay. Now you can see that this angle here, which is theta 2, what is theta 1? Well, here we could have worked it out, and it's probably about 40 degrees. This one will be about 70 degrees. What is this angle, theta 1? What is this angle, theta 1, in air? And it's a right angle. So about 40 degrees, theta 1 becomes 90 degrees. And that's just like the borderline angle where the light is mostly refracted, and this ray of light comes out here. After that 40 degrees, then there is a reflection taking place. So if this purple angle all the way around there is 50 degrees, going the other way, all the way around, reflection angles are equal. So that angle all the way around there would be 50. So this has gone from, I don't know, could work it out, 30, 40 degrees. This green one is coming out at about 70. This one here is being refracted. All these three are being refracted. Orange one goes to 90. These are all refracting angles, but this one doesn't come out and get refracted straight away. It reflects before it comes out, and that is not refraction, that is reflection. And it's all of the light is internally inside the block, is internally reflected. So I'm going to jump now to ray 4. I've missed ray 2, doesn't matter. Ray 4. The angle inside, remember, this is theta 2 inside. Above, anything above this 40 degree, so the 50 degree beam, which is bigger than 40, 20 is less, 30 is less, 40, something important's going on, comes out along the edge there. 50 is reflected. The 50 degree beam is totally internally reflected. And then it's not a refraction thing. Snell's law is all about refraction. Reflection's dead simple. There's no signs involved. If the angle there is 50, the angle for this purple beam is 50. If this went up to 60, the angle there would be 60. So the angle coming along here would also be 60. All of the ray is totally internally reflected. Okay. Now, what's important about this one, this beam of light here, where it just comes out at 90 degrees, that angle, which is about 40, that angle is called the critical angle. And the critical angle inside the glass matches up with a 90 degree angle, go around there, 40 to the orange, all the way round to this one, 90. After that, as that angle gets bigger, it's all totally internally reflected. This angle, which is about 40 degrees, is called the critical angle. It's the changeover angle from coming out there to staying in there. Okay, so I'm going to write this down. I haven't written much down recently, but I'm going to say that this angle here, theta 2, has become what's called the critical angle, and we have a new symbol for the critical angle, and it is theta c. Okay, so this would be theta 2 is 20, this is theta 2 is 20, this is theta 2 20, 30, this is theta 2 40, but we're going to now call it not any old angle, we're going to call it the critical angle for coming out at 90 degrees. Anything bigger than the critical angle stays totally internally reflected. Theta 2 has become what's called the critical angle. And what's the definition? The definition of critical angle is the angle of light inside a medium. So the light here is inside, not really interested in this bit outside because it's all straight anyway. So it's the angle inside, which we've measured to be about 40 degrees, the angle of light inside a medium which allows the light to exit into the air at 90 degrees. So if that's about 40 degrees, the angle either here, the angle all the way around, normal's disappeared here, but the angle all the way around from the normal is 90 degrees, or the angle all the way from this normal is 90 degrees. They're both exactly the same. Allows the light to exit into the air at 90 degrees. And the beam exits along this is called the glass, that's glass in there, this is air, this is called the glass air boundary. The beam exits along the glass stroke air boundary. And that's the definition of what the critical angle is. Right. Now there is an equation that goes with the critical angle. It's not just a load of waffle, which I've spent quite a bit of time on, but there is an equation that goes with it. I'm going to rub out the whole lot. I was just thinking whether I should take a picture of that first, a still picture, but no, I won't. So I'm going to rub all that out, and there is an equation that goes with the critical angle, which I'm going to cover now. Okay, now we already know from Snell's law, video 2 from Snell's law, n equals sine beta 1 divided by sine beta 2. Okay, so which one is which? Theta 1 is always the angle outside in the air. And theta 2 is inside the medium. Because when we did this before, and we were doing it like this, and we had this beam of light doing that, this is theta 1, this is air, and this is glass. So theta 1 is in the air, and theta 2 is in the glass. Now with that semicircular block there, okay, we're starting with the beam of light already in the glass, and then it comes out along there. So this, the angle in the glass inside, is theta 2, and this one, this angle here, from the normal right round to the ray, or it could be from the normal right round to the ray, this is 90 degrees. This is 90 degrees as well, because the angle on a straight line is 180 degrees. So theta 1 is 90 degrees. Okay. Now, if you put 90 degrees into your calculator and take the sine of it, the sine of 90 degrees is equal to 1.000. It's just 1. It's just equal to 1. So what I can do is I can take this formula here, n, is sine theta 1 over sine theta 2. Sine theta 1 is equal to 1, because I've said that sine of 90 is equal to 1. What's special about this angle theta 2? It's the sine of the critical angle. It's not just any old angle. It's the sine of the critical angle there. Okay, so I can take my standard Snell's law. Theta 1 outside is 90. This theta 2 has become the critical angle. The critical angle is the angle at just when the beam of light exits at 90 degrees. And I can rewrite that if I want, and I can have sine theta c is equal to 1 divided by the refractive index. So that is a formula, which I think it's that version, which is on the data sheet. the sine of the critical angle is 1 over n, which is just a rewrite of that, and that has come from there, where you put theta 1 is 90, and theta 2, we're not going to call it theta 2, we're going to call it the critical angle. And I've said it is about 40 degrees, but I didn't qualify. I have qualified that by saying is about. I'd actually like to work out now what it really is. So I have got the sine of my critical angle, which I've told you is about 40 degrees, is equal to 1 over n, where n is the refractive index of glass. Now we know what the refractive index of glass is. For glass, the refractive index n with a G for glass is equal to 1.5. You can go away and look that up in the data table, okay, on the data sheet. So what is the critical angle? So I'll take that formula from the data sheet. Sine theta c is equal to 1 divided by 1.5. So what I can do now is I'll take my calculator and turn it on, and I can do 1 divided by 1.5 equals, and that is equal to 0.6666. This is not the final answer, but it carries on, and it's a recurring number. All right, I'm not going to put the recurring dot. Physics, they don't like you to put the recurring dot, but it will go 1.666, and eventually it runs out of space on your calculator, and it does turn the last figure into a 7. Okay, so I've got sine theta c is 0.66, and I'm going to keep that number in my calculator, 667, whatever it is. So if I do theta c, if I want to find out what theta c is, I do sine to the -1 of 0.666, whatever it is in my calculator. Okay, and I do shift sine inverse of the answer equals, and you can do this yourself, you'll need to do this yourself, and it's 41.8 degrees. It's actually not 40. I said it was about 40. It actually works out to be 41.8 degrees. Okay, so you now have an example of working out what is the critical angle of light in glass. So what's the critical angle for light in other materials? And you can now spend a bit of time for looking at other materials. You get all these different numbers. Glass is 1.5, water 1.33, diamond 2.42, and so on. And so you can work out the critical angle for any other material you like, as long as we start with our sine theta c is 1 over n for whatever material it is. So for diamond, we already know that n is 2.42. So you can do sine theta c is 1 over 2.42. And you put that in your calculator. And that works out to be 0.413 something or other. You do the inverse sine. Theta c is the inverse sine of 0.413, and that comes out to be 24.4 degrees. So for glass, I've got critical angles, so I could make up a table, and I could just carry on critical angle table. You don't get given this, you'll have to work all these out if you wanted. So I've got diamond, it's 24.4, and of course remembering that the refractive index, the matching refractive index is 2.42. I've got glass, that's degrees. I know it's 41.8 because we did that before, and the refractive index for glass was 1.5. I can do the same for water. Let's just do that quickly. Water, what's the refractive index of water? It's 1.33. So I get N is 1.33 from the data booklet. Sine theta C is 1 divided by 1.33, blah, 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 blah. And theta C for water comes to be 48.8 degrees. So I'll put water into my little table up here. 1.33 is the refractive index, 1.33, and water, the refractive index is 48.8 degrees. So what can I conclude from that? The bigger, the larger, the bigger the refractive index, the smaller the critical angle. Conclusion is the larger the critical angle, the smaller the larger the critical angle, the smaller the refractive index, smaller the refractive index. You could say this the other way round. Okay, the larger the critical angle, the smaller the refractive index. You can have it round the other way if you want. But as one gets bigger, that's getting larger, this gets smaller. Larger angle, smaller refractive index. Larger refractive index, smaller the critical angle. You can have it either way round as you want. Okay. Higher the refractive index, the smaller, or lower, the smaller the critical angle. In the material, whatever the material is, the critical angle in the medium. Okay, so inverse, what's called an inverse relationship. This is large, this is small, this is small, this is large. That's an inverse relationship. Now, apparently, the reason why diamonds glitter so much, if you see a diamond, probably the only place you're going to see real diamonds is in some sort of ring, like an engagement ring or a wedding ring. The reason why diamonds appear to glitter so much and sparkle so much is that they have a high refractive index and a small critical angle. This used to be in the syllabus, but diamonds, when they're cut, are cut like this when you look at them from the side. And this would be the shape of a diamond. This would be the top. And what happens is that light comes in and it's got a small angle of critical angle. So it comes in, and what happens is the light comes in and it bounces off. It internally reflects off all of these different faces here, and the light comes on and it does a sort of bouncy thing like this. And eventually comes back out again. So if you hold a diamond up on a ring to the sunlight, you'll see the sunlight comes in, reflects totally around inside the shape of the diamond and comes back out. If you do this with ordinary glass, the light comes in, but it doesn't come back out again. And glass or fake diamonds actually look quite dull. So it's one way you can tell. Experienced jewelers can tell immediately just by looking at the way the light shines off something whether it's a real diamond or if it's some sort of fake diamond. Fake diamonds are often made of glass or some other material, and they're called paste. You don't need to remember that, but an experienced jeweler will be able to tell just by looking at the sparkle whether it actually is a diamond or whether it's some sort of fake stuff, because the light doesn't come back out. It doesn't totally internally reflect and come back out with materials that have a bigger critical angle and smaller refractive index. Okay, so I ought to write that down just to finish off. So diamonds have a low critical angle, which produce more total internal reflection within the material. As in the diagram that I had, the light comes in, it reflects all the way around, totally internally, comes back out. So the light re-emerges back to the viewer or the wearer of the ring. So if the light comes back out, the diamond actually appears to be quite bright because you get the light coming back out like a little tiny torch beam. And so the diamond appears, especially when you move it, and you're holding it, you're wearing it, and you hold your hand in a different direction. So the diamond appears to sparkle. It appears to be quite bright. And it also, actually, when that happens inside the diamond, you also get a little bit of the light splitting up. White light, mentioned this right at the start, I've still got to come onto this. White light actually gets split up inside materials that are prism shaped, and a prism we had at the start was just a simple triangle. A diamond upside down is a bit like a prism shape. And in fact, that's a bit like a raindrop. And what happens with all of these things is light comes in and comes out again, having been split up a little bit into the different colors of the rainbow. A raindrop is, a classical picture of a raindrop or a teardrop is also some sort of prism shape. So the beam of light goes in and comes back to you. Doesn't with a prism, but it certainly does. The light comes in and bounces back and comes back out again. And the same with a raindrop. The light goes in, and because of the angles, it comes back out again. And you see the light also re-emerging as a rainbow. That's because you get this total internal reflection. And the jeweler who cuts the diamonds don't come out of the ground in that sort of classic shape. They have to be cut and prepared and polished, so they have this sort of prism shape. If you see this prism shape of glass, we know the light comes in there and it comes across and it comes out. Whenever the light comes back out of these materials, it tends to be split up. Here, the light, you've got to be in the right place. The sun needs to be over here and the viewer needs to be this side. The sun needs to be here and the viewer is this side. The sun with a prism is this side and the viewer is that side. And so the diamond appears to sparkle, and I'll now rub that bit out. And what do you see? Not only does it sparkle because the light goes around, it's totally internally reflected, it gets split up. The colours of the visible spectrum, and the colours are Ruyger-Biv. They're seen, and that's what produces the sparkle. So there's a little bit of writing just about diamonds. I think that's about all you really need to know about diamonds. And that's about it. I'm not going to do, oh yes I am, I'm just going to do one last thing. A graph. What does the graph look like of not the angle but the sine of the angle? What do the graphs look like when you plot refractive index against the sine? Okay, so graphs. Just to finish off with, we've got, if I have n, the refractive index, it's an inverse relationship, sine theta c. And you've done inverse relationships. Probably the best known inverse relationship that you've plotted a graph for is at National 5 with Boyle's law, and you get a graph that looks like that. And you then plot the inverse. If I then do the inverse at National 5, this was pressure and volume. But if we then plot refractive index against 1 over sine theta c, this is what happened at National 5. Pressure against volume gives you this inverse curve, but pressure against 1 over the volume, and in this case refractive index plotted against 1 over the sine of the critical angle, gives you a nice straight line. And so you've got a relationship there which you can easily put into some sort of formula, which you've already got, and you've got the formula is n equals 1 over sine theta c. There you go. So it's inversely proportional to sine theta c, or directly proportional to 1 over sine theta c. And I think that's just about that to finish off with. The next video I'll try and post up. Won't be posting it up too soon. I'm going to take a break now. I'll pause this one. I doubt if people are keeping up with me. You might be. As soon as you finish one, you go on to the other. But you've got all the problems to do as well. You've got the practice problems to do in the course notes. You've got the Campbell-Robertson problems. And there's a whole heap of the Campbell-Robertson questions that you need to do. There's dozens from 80 something to 100 and something. And hopefully you'll find a way through this of breaking this up into chunks. Don't try and do the whole thing all at once. You really want to chunk it, break it down into these little sections, watch the videos. Apologies that I didn't manage to do the videos first, but you know why. It's because I've been in school, and you can't do both in school. But now I'm at home and I'm just rattling through all of these in one session. It's now nearly 1 o'clock. I've been on the go doing this since 8:30. It's going to take you a long time as well. That's about 4 hours of videos I think I've produced. And it will take you at least as long to copy all that down and then start having a look at the problems if you choose to do it that way. Okay,